Okay, let's get started here. So this is welcome. This is the LaRouche Pack Saturday night discussion. It's kind of wrapping up a 5-week course series on the question of physical economy and platforms. And tonight's presentation will be by Ben Deniston, and I'm your host for the discussion tonight, Mike Steger. Just as a brief introduction to a question, and this economic question is the defining issue of the country. There is an ongoing realignment politically. There was mention in our discussions earlier today of a Newsweek article pointing to the fact that this insane progressive left, the Black Lives Matter, the hardcore eco-terrorists, the pornography in kindergarten, all these questions that are now manifesting itself in the political discourse of our country, not surprisingly, are terrifying to the overwhelming majority of the American people. And nearly 80% of the American people wouldn't give $50 a month to stop climate change. 50% of them wouldn't give $10. So when you look at gas prices, when you look at the inflation, when you look at the shutdown, there's a shutdown of the final last nuclear power plant in California. It's might as well, turn California into a graveyard, with talk of replenishing this kind of nuclear power plants with floating windmills offshore. The whole thing is just like some crazy clown show. And what used to be the most industrial and advanced agricultural and industrial economy with incredible scientific research capabilities in the world 50 years ago. And that 50 years, we've seen the dismantling of the United States. And that's where we're seeing a political fight. You're seeing a political fight because for 50 years, they've rammed down this globalization neoliberal system. They've pushed the eco climate anti-industry program. They've pushed the postmodernist educational system. And it's failed. It fails to support a population. It's not just in the United States. In every major developed nation in Asia, Europe, and in the Americas, you see a collapse in population. You see a collapse in the optimism towards the future. And the only way to address that is on two questions. One is a higher scientific and artistic sense of mankind. And that's what Mr. LaRouche, our founder, really presented. And the other is to support that with a real perspective of how you develop human society over the course of multiple generations. And that's what we see the American people mobilizing around. That's what Donald Trump has brought to bear in terms of a political discussion. People say, some people think that people that support Trump are waiting for Trump. Hardly. It's such a ivory tower view that many people have, especially those in Europe and other places in the elites of the United States who think people are waiting for Trump. That's what they were doing with Obama for far too long. But the reality is the American people are out mobilizing. Trump's out mobilizing. There's a kind of ferment in the country where profound ideas around where we go as a species and what we do as a nation to develop our country are more alive than they have been in decades, if not generations. And so I think that's where things stand. We'll have one of Trump's first speeches will be tonight. That will be interesting to see to what degree he brings in an economic perspective. There is discussion of a new Republican platform. And to a large extent, what we do here in these discussions and what you do in helping to organize with these ideas directly feed in to a question of a program for the country. And it's a program that can't just be for one presidential term or an election cycle. We need a program that looks at minimally 25 and preferably 50 to 100 years of where do we want to end up as an economic platform for the nation. And in that regard, I think that's what Ben's going to address tonight. So I know, Ben, you probably have more to say on the drought, so I don't think I need to say much on that. I'll just hand it off to you and we'll get the discussion started.
Thanks, Mike. Glad to be here again. Glad to be here with everybody. Like Mike said, me taking up the question of the drought in some detail. I'm sure people have heard, especially if you're on the West Coast, of the increasing severity of this drought situation. So we're going to look at it a little bit from the standpoint of what we developed in this class series on economic platforms and a real higher conception of what economy needs to, how we need to understand economy. And this has come up a little bit in some of the previous discussions in this class series, just how kind of polluted and disliked the subject of economics tends to be in the population, because what people get presented with is, often very banal or just outright wrong. And so the situation is ripe, and it's necessary that we introduce these higher conceptions of economy, because you're really talking about, exactly like Michael was saying, how we progress as not even just a nation, but as a species, as mankind. It's really the essence of what makes the human species absolutely distinct from animals and animal life. So this issue we've been taking up in this class series, we're going to continue to develop this, and this really has to be a critical core component of a movement that's going to be able to save the country. And in that context, Mr. LaRouche's work is key. And today we're going to take up some of the issues around the drought crisis in the West. So I'm going to jump over to share some slides here to visualize a little bit of what we're talking about. So I think we're good here on this slide screen share. So again, this is the 5th class in this series on the Western water crisis. So if people haven't seen this, this is a depiction of the severity of the drought as of June 1st. This is a product that's updated weekly, that's put out weekly by the US Drought Monitor. It's a relatively useful place to go to get an assessment of the historical records of drought for the last decades and the present situation. As you can see here, obviously the red is more intense. The red color is more intense drought. That darker red you see throughout certain regions of the West, that's the most extreme form of drought. And so the situation is getting worse and worse in 2021. It really exploded. I'm not going to take a whole lot of time because this is being covered plenty in the news, but just to give you a sense of the severity of the situation, one of the 2 major water distribution programs and infrastructure systems in California, the California Central Valley Project, recently announced that they were going to be delivering 0% of water requested for agriculture. A few weeks ago, they had said it was going to be 5%. Now it's 0%. So this is an absolute crisis for agriculture in California. 0% of the water requested to sustain agricultural activity is going to be allocated, and only 25% of the normal annual allocation is going to be given for municipal and industrial uses. This particular project, the California Central Valley Project, if you're not familiar with it, it supports 27 million people and 750,000 acres of farmland. And it's been consistently under-delivering to the needs of the population. And there's another headline that I thought was interesting, just another dimension of this. Because of the low water levels in the reservoirs, et cetera, there's going to be a big impact on hydroelectric power. Now, Mike just mentioned this insane process of now they're trying to shut down the last nuclear power plant in California, and then you're going to be hit with reduction in the hydroelectric power capabilities. I mean, this is just going to be another disaster for California. Rolling blackouts, I'm sure, is going to be extremely likely. So this coverage stated, California is at the risk of energy emergencies during periods of normal peak summer demand and high risk when above normal demand is widespread in the West. And this is due to the hydroelectric power shortage, which is going to be coming because of the lack of the water availability. You step outside of California, obviously California, the most populous state, maybe gets a little more attention, but in general, it's the whole Colorado basin is extremely drastically hit, and this extends all the way out to North and West Texas, out to Colorado, and even up into areas like North Dakota. Regarding the Colorado River system, it's been said the past 12 months have been among the driest on record across the Colorado River basin. Some of the coverage goes on to say Lake Mead is now just 37% full, heading for a first ever official shortage and sinking towards its lowest levels since it was filled, since the reservoir was originally created. And Lake Mead represents about 1/3 of the entire storage capacity of the Colorado water management system. So this is highly significant. But it's important to note that this is not new, right? And you could go on, I mean, you could talk about specific situations in agriculture, certain communities are going to be hard hit. I mean, there's a lot to go over on that, but I think it's worth stepping back and realizing this is not just something that came out of nowhere. Our organization, Mr. LaRouche in particular, have been campaigning on this water issue for decades, the situation, the water needs of the West. And what we're seeing is just the reemergence of a continual, slowly increasing crisis that's been developing for the past really couple generations. There's been a complete failure, especially since the United States abandoned the kind of pro-development, pro-infrastructure policies represented by John F. Kennedy, represented by Franklin Roosevelt, represented by Abraham Lincoln, the kind of policies that really built this country. We shifted away from that dramatically in the late 60s, early 70s, and we failed to continue to develop the resource supplies needed to address situations like this. And the water crisis is just an extremely prominent and challenging example of that process. So if you look at the longer term situation, this is a map depicting groundwater depletions in aquifers over the past century, basically. And again, as you might expect, the red is a more intense drawdown of the aquifers. Orange, various shades of orange to yellow is slightly less intense. But this is giving you a depiction of the cumulative drawdown of the groundwater supplies, which provide a substantial portion of the water for many of these regions. You have things like these reservoirs, like Lake Mead, like we just talked about, which is created by the Hoover Dam. California has a number of reservoir systems, right? That's part of the water delivery. Another substantial source of water, even in the West, is groundwater supplies, which are getting drawn down year after year after year, more and more and more. So the water, the groundwater supplies are getting, you have to go deeper and deeper and deeper to access the water, and it's getting more and more difficult to access these groundwater supplies. So this is something, again, that's been developing for quite some time. And just to give you a sense of the scale, if you take these three regions, so the Central Valley, California Central Valley Aquifer region highlighted there. On the other side, in the center of the country, you have the High Plains Aquifer, which contains the Ogallala Aquifer, stretching from South Dakota down into northern and western Texas. Major source of water for this High Plains region. It's been drawn down substantially. And then the Colorado River Basin, generally shown in the middle there. If you take these three regions and you just take the average annual depletion of groundwater from these three regions, it's about the same as the flow of the entire Colorado River. So we're basically drawing out of groundwater stores the equivalent of an entirely additional Colorado River's worth of water flow year after year after year continuously as a rate of depletion of these aquifers. So it's a significant issue that's been building for some time, but there are solutions, and that's what we're going to get into. So in a certain sense, this becomes a very useful case study in pedagogy to go back to, again, Mr. LaRouche's unique insights into physical economy. The basic question of what is a resource. You tend to get the idea that we're just drawing down resources, we're using up resources, and they're just gone. But that is not the case. Human development comes with the creation of completely new resource bases. Through scientific discovery, we can come to understand the principles governing the natural world as we experience it, the principles acting behind what we experience, controlling what we experience. We develop that kind of knowledge through discovery of scientific principle, which allows us to change our behavior, change our action, and develop entirely new resource bases, and really eliminate the idea of limitations to growth for mankind. And water is an excellent example of this, right? There's not a fixed amount of water, even in these groundwater supplies. It's all part of a system that we need to understand better and develop better, and we can have all the water we need. So the framework I want to use to discuss this is just a basic understanding of the water cycle, right? So here we have an animation just showing the basic characteristics of the global water cycle. You have sunlight evaporating ocean water, right? Most of that evaporated ocean water falls back over the oceans as rain over the oceans. A relatively small percentage of that comes over land. And that becomes the basis of the entire water cycle over land, is what gets evaporated by sunlight and precipitated over the continents as rainfall over the landmass. But once the water is over land, something interesting happens. Again, here we see the input of the relatively small percentage of all ocean water that's evaporated, brought onto land. Some of that water, as you see here, gets re-evaporated and brought back up and falls again as new rainfall over land. Other of that water gets brought back up into the atmosphere through plant life, specifically through a process called transpiration, where plants in the process of photosynthesis end up releasing a significant amount of water vapor back into the atmosphere, which becomes a new source of rainfall over land again. And if we look at the actual figures on this, these come from various studies attempting to understand how the water cycle works on a global scale for the global water cycle in its totality. We can get a sense of the different contributions to all the precipitation on land, right? So here we see only about 10% of the fresh water that gets created through the evaporation of ocean water ends up falling over land as precipitation over land, only about 10%. So most of the water that gets put up in the atmosphere by the actions of the sun through evaporation ends up falling back in the ocean. Only about 10% comes down over land. About a quarter of that much ends up getting re-evaporated and falling again as new rainfall over land, whose source was water evaporated from the land itself. But an even higher amount comes from specifically plant life through this transpiration process. So we put figures on it. Over half of all the rainfall on land comes from water that was put in the atmosphere by plant life specifically. Or said another way, if plant life was not acting, photosynthesizing, transpiring the water back into the atmosphere, it would basically cut the rainfall over land in half. So as soon as you're talking about the water cycle and water availability, you're immediately taken to the question of mankind's interaction with the biosphere as a system. It's not just solar evaporation and rainfall. You're talking about the interaction with life and the system of life in its totality, which takes us to the work of a very interesting figure named Vladimir Vernadsky, who was the really originator of the concept of the biosphere, which is probably what he's more known for. But his understanding of the biosphere provides a very useful framework to address these questions of water, resources, and economic development. He said, if you want to understand the biosphere, you first have to understand the lithosphere, which is basically a planetary body devoid of life. So here we have a picture of Mars. This might be a good representation of what a basic lithosphere type system would look like. You do have weathering. You do have certain activities going on, impacts from the solar system, volcanic activity, various things. So, but you have a certain process of development on the planet, which is purely abiotic, purely the product of planetary systems interacting with the cosmic environment. That's the nature of the lithosphere. And then he says you have to understand the biosphere as a process that in a sense is acting upon transforming, developing this lithosphere system. So you have the lithosphere, abiotic, non-living planetary planet. And then acting upon that, you have this far more powerful in terms of rates of transformation, effects on chemistry, effects on the material makeup of the planetary surface, effects on the atmosphere, far more powerful system called the biosphere. So in terms of total mass, total weight, the biosphere is the total amount of living matter, living organisms on Earth is minuscule compared to the lithosphere itself. And yet it represents a far more powerful actor in transforming and shaping the surface of the planet, again, its chemistry, the atmosphere, and so on. So this is and again, we saw this with the case of the rainfall over land, right? The biosphere literally doubles the amount of rainfall available over land through the process of plants in the process of transpiration, right? But then you have another domain, a qualitatively higher domain, which Vernadsky called the noosphere, which is the domain of human activity. And the noosphere acts upon the biosphere and acts upon the lithosphere. So the noosphere, this domain of human activity, human development, is another qualitatively distinct step in this process, but again represents a far more powerful force than even the biosphere itself. The domain of human activity, science, culture, societies, shaping the biosphere using our understandings of agriculture, water management, et cetera, and so on, to improve and develop the conditions of the biosphere. So this is Vernadsky's basic thesis for understanding these domains of science and understanding mankind's condition and situation in the natural world. You have to look at the relation between these successive hierarchical systems. And to take it one step further, they're not static systems. They're developing, they're changing, they're increasing in energy flux density, something we touched on in a previous class a little bit. We discussed it more from the standpoint of human activity and economies and productivity, et cetera. But it's also an expression you see in the evolution of the biosphere itself. An increasing energy flux density as the biospheric system becomes more powerful over evolutionary time. This is just kind of a fun depiction of the geological timescale, the evolution of life throughout the history of the planet Earth. You might want to pull up this image and look at it a little more closely at another time, but it's just a depiction of the evolution of life from the first most primitive single-celled organisms to the beginning of the development of multicellular life, to the development of life that could begin to move onto land, early types of amphibian type life into reptilian types of life, which is a qualitative transformation. Everyone's familiar with the age of the dinosaurs, the mass extinction into the age of mammals, that through this evolutionary process, life has actually become more powerful. And the biosphere as a whole has increased in its energy flux density and increased in the rate at which it transforms and shapes the surface of the planet. So it's not a steady state process. There's no steady natural balance in the environment, in the natural world. It's a process of development vectored towards increasing energy flux density. And mankind, again, comes in on top of that as a more powerful and more significant force than even the biosphere, through our power of wielding creativity, scientific discovery, culture, and the development of societies. So this is just highlighting a relatively new study, just came out in April, which I thought was just kind of interesting. I don't know if other people had indications of this, if this was the first time this had been published or proven or not, or if this has kind of been something that's been somewhat known for some time. But this study showed that over at least the last 12,000 years, so basically going back all the way back to the last ice age, most of the landmass, most of the terrestrial planet had been shaped by human activity. Nearly 3/4 of all land on Earth had been, again, not just in the past 50 years, not just in the past 100 years or 200 years, but you go back thousands of years, 12,000, for at least 12,000 years, even in these relatively early forms of society, mankind had become already the dominant force shaping nature for nearly 3/4 of the entire land mass of the planet. And they show that it actually, human management and development of territories over these time periods actually led to increasing biodiversity, in a certain sense, more productive, more diverse, more developed natural environments, which is a rather interesting point to make. And they go on to promote some of the current Malthusian views that we're supposedly causing, major problems for the biosphere today. I don't buy that. It's a whole nother subject to get into, but just highlighting this aspect of their study, I thought is relatively interesting from the standpoint of the work of Vernadsky and what we're talking about, right? So you have this nesting of successive systems. As we highlighted, this is how you need to begin to look at the water cycle, the water system, water availability, and water as a resource, right? So there's not a fixed amount of water, it's a cyclical system. It becomes a question of how well can we manage and improve that cycle to increase the productivity of the water cycle as a whole, regionally, on continental scales, and on a global scale, right? That's what we should be thinking about. How can mankind increase the productivity and the usefulness of this cycle, right? We're not going to use up the water. I promise you, there's plenty of water, right? It's a question of how productive can we make that water cycle. So there's a few ways we can act on the water cycle. 3 main ways we're going to look at here from the standpoint of this illustration, this diagram. The first is taking what we see highlighted here, which is the river runoff, right? You have the evaporation of ocean water that provides the basis of all water on land. That water on land recycles into the atmosphere, falls back as rain again in many cases to a significant degree, and eventually finds its way back out into the ocean through rivers that run back off into the ocean, right? So the first question is, how can we develop and improve these river systems and improve the amount of productivity and biospheric activity and human economic activity that's generated by this water while it's on land before it returns to the ocean. And the Western United States is an excellent illustration of what could be done in exactly this way. So here we have the total freshwater river runoff for the northwestern and the southwestern regions of the North American continent, right? The actual boundaries you're seeing here, the blue area, these are determined by river basins, right? So these are areas where any water that falls within a watershed area will end up making its way to a certain particular river, and that river kind of defines a basin, defining certain physical natural boundaries in the territory of the West, right? So if you take in blue the Northwest basins, right, up to Alaska, the Yukon Territory, British Columbia, Washington, Oregon, Idaho, right? You have a very significant amount of freshwater runoff. And particularly along the coastal regions, British Columbia, up into Alaska, a significant amount of that freshwater runoff spends very little time on land. It tends to get deposited because of the geographic territory in the high mountain ranges along the western regions of the continent. It tends to not get deposited very far inland and tends to run off as very large rivers back into the ocean with spending relatively little time on land. So there you have the total annual freshwater runoff of all these northwestern rivers has been estimated to be about 1,510 cubic kilometers per year, right? Relative to that, the Southwest, significantly less than 1/10 of the freshwater runoff availability. You have the Colorado River, you have a few other smaller rivers, you have the Sacramento, the San Joaquin rivers in California, you have the Rio Grande coming out in Texas, and not a whole lot more, a few smaller rivers in Mexico. And you can see the total water availability, the total water runoff for the Southwest is around 115 cubic kilometers per year. So huge discrepancy between the water availability in the Northwest and the Southwest. But how productive is that water? What gets done with that water? Well, we did a study a few years ago, which I thought was pretty interesting, where we looked at the total amount of biological activity, photosynthetic activity, basically new plant life that gets created every year in these different regions, right? In addition to the Northwest and the Southwest, we have the High Plains region identified in green there. So you can see in the Southwest, you have, I don't know, a bit less than half, between a half and a third of the total amount of photosynthetic activity being generated in the Southwest compared to the Northwest, right? But things get a little more interesting if we look at the productivity rates of these different regions relative to the amount of water availability and water flow. And here we see that the Southwest is actually the most productive region, right? Although the total amount of photosynthetic activity, the total amount of biological activity, biospheric activity in the Southwest was, again, between around between a third and a half of what goes on in the Northwest. The amount of water that's done with is significantly less, right? Less than 1/10, maybe like a 15th of the entire water flow availability. So the actual productivity of the water cycle in the Southwest is far higher, right? The amount of biospheric activity supported per unit of water flow per year in the Southwest is around 5 times higher than the Northwest. So here you have the introduction of something like NWAPA, the North American Water and Power Alliance. So this is the idea of redistributing something on the order of maybe around 5% of the freshwater runoff in the northwest regions, and bringing that down through the continent into the southwest, into the high plains, connecting to existing water systems, the Colorado system, Colorado River system, et cetera, and basically addressing, for the most part, the entire water needs of the Southwest and the high plains and northern Mexico. So this was an actual proposal that was designed in the 1960s. If we'd continued the kind of pro-development policy, this certainly could have and should have and probably would have been done well before the turn of the century, and we would not be in the current crisis we're in now. But this is an illustration of the kind of large-scale water transfer system where you take, again, 5%, a relatively small percentage of the abundant fresh water flow from the Northwest, and you divert it into regions where it's needed, and then allow it to, make its way back into the ocean again, right? Because you're dealing with a cyclical system, increasing the productivity of the entire territory. And we did some rough estimates of what this would do to the biospheric productivity, what it could do. And if just this 5% of the water runoff from the Northwest was diverted to the Southwest through Nawapa into the high plains, you could significantly increase the total biospheric productivity, the amount of greening of the Southwest region of the United States and into northern Mexico, resulting in potentially, assuming the productivity rate is the same for the Southwest with that new water being brought down, you could look at basically a 30% increase in the total biospheric productivity of the water cycle in the western half of the continent through something like Nawapa, right? Very fascinating study, a very fascinating way to look at it, right? 5% redistribution of existing water flows applied into the Southwest at the rate of biospheric productivity and economic productivity more generally of water in the Southwest, and you get a significant boost, maybe up to 30% of the entire biospheric productivity of the water cycle in the western half of the continent in its totality, right? So here's maybe a just illustration of conceptually what that looks like, right? You're acting on the freshwater runoff, you're redirecting a fraction of it back up onto land before it runs off. And that's one way mankind can augment and improve the productivity of the water cycle. So Nawapa, or variations of it, taking some idea of redistributing the much more abundant and immense freshwater availability in the river systems in different parts of the continent and bringing those to the West, is one aspect of the type of thing we need to address the water crisis. The next dimension of mankind's interaction with and development of the water cycle is acting more directly on the ocean water itself, desalination, right? Not just taking water that already exists on land and redistributing it before it runs off into the ocean, but going directly to the ocean itself, bypassing this whole process of waiting for the sun to evaporate the water, hoping the evaporated water in the atmosphere precipitates where we want it to precipitate over land. We can go directly to the ocean through advanced technologies of desalination, remove the salt, create fresh water directly, and increase the water supply that way, right? And this is a technology that's been known for decades and it's been improving, becoming more efficient over time. These are images. This is an image of a desalination plant in Spain. There's a very efficient, very new plant in Carlsbad, California, that came online just in the recent few years. There's plans to develop additional desalination plants potentially in California, right? So this is another major step that can be taken to address the water needs of the West. And we did a bit of a study on this a few years ago looking at California in particular. And if you look at just the water needs for the state of California, and you look at the water needs for municipal, cities, towns, for the general population, placing to one side for now, for a second, agriculture. 65%, 2/3 of the population of the state lives in a relatively small area of the state, Southern California and the San Francisco Bay Area, right? So you could conceivably, with really not that much of an increase in the total energy consumption of the state, provide a significant amount of desalination. If we were to build a significant number of large-scale desalination plants, and you could, provide the water needs for these coastal regions directly from desalination, right? So according to this study here, we were looking at, you're looking at maybe about around 10-12% of the total water needs of the state come from the needs for these major metropolitan areas along the coast. So if you were to provide desalination in these particular regions to address those needs, that means that would have a spillover effect back further inland, where water that's currently being directed from rivers, from the Colorado system, from the California water projects, San Joaquin, the Sacramento rivers, et cetera, could be used for other purposes, for agriculture, for water needs further inland, et cetera, because you wouldn't need to direct that water to these coastal regions, because you can provide that supply with desalination of seawater on the coast, right? And then here's a schematic of additional places where we could potentially use desalination, not just on the coast, not just for ocean water, but also inland, where you have places where you do have water, but it's not really usable because it's brackish water, there's salt in it, you can't use it for agriculture. It needs to be cleaned one way or another. So you could even significantly improve the water supplies further inland through the development of desalination and water management technologies, as depicted here. So the third dimension of acting on the water cycle, of managing the water system. This is a depiction of where what desalination looks like conceptually, again, in our illustration of the water cycle, right? So we have a new tap directly into the oceans, bringing that water onto land as fresh water and increasing the total water availability in the terrestrial water cycle through the development of desalination systems, right? So this is how desalination conceptually fits into our mankind's augmentation, development, and management of the water cycle, and improvement of the water cycle. So the third aspect we can talk about, the third dimension of managing the water cycle, is weather modification. And in particular, looking at technologies that use ionization systems to help accelerate the rate of precipitation of water that's already in the atmosphere. So this is a very interesting technology, not as well known as things like cloud seeding, but has been demonstrated in a number of cases and shows very interesting results. The way these systems work is you're basically setting up towers which hold high voltage lines through which you run a high voltage current to create a direct ionization of the local atmosphere, local air, which will then, in that local environment, help to increase the rate of condensation of water vapor and increase the rate of precipitation and rainfall in areas where you have these things operating. And the actual amount of total energy required for these systems is actually extremely low. So they actually represent a very efficient and interesting technology. And some of the science of this gets into a lot of interesting areas about the actual true causes, true sources of climate change through the activity of solar activity and other cosmic influences on our planet, which maybe we can get into in the Q&A a little bit if people are interested. But there's a whole domain of science here that's really fascinating. So these technologies have been demonstrated multiple times, independent companies, independent operations all over the country, significant operations in Mexico, Australia, Israel, United Arab Emirates, Oman. Russia is one of the places where this technology was first really developed, all the way back to the 80s. I want to highlight just one particular company which has done some pretty interesting work. It's called Australian Rain Technologies. And between 2013 and 2018, they ran a series of trials in Oman. And they got consistently 16 to 20% increases in rainfall and precipitation each year of the trials. And they did an extensive amount of work with sampling stations, advanced statistics, various ways to measure what the rainfall would have been, should have been if the systems were off, when they were on. And they did an extensive amount of work to try and demonstrate beyond any shadow of a doubt the validity that these systems were actually increasing the rainfall. So by very conservative estimates, in a very robust series of tests, they demonstrated 16 to 20% increases in precipitation with really just a handful of systems in this very dry desert area in Oman. Again, so this is just one place where the technology's been demonstrated and developed. Other places around the world have done similar trials and had similar successes and results. So how does this fit in with our conceptual illustration of the water cycle? Well, here we're tapping directly into additional water vapor stores in the atmosphere and helping to ensure that that can precipitate, fall over land where we want it and when we want it. And when done right, this can even help to draw additional flows of atmospheric moisture from over the ocean and help to draw that inland and actually increase the total amount of water availability to precipitate over land than would have been the case otherwise. And again, if you recall the figures and the breakdowns from earlier, only about 10% of all the ocean water that's evaporated ends up falling over land. So 90% of the ocean water that gets evaporated, put up in the atmosphere as water vapor, is sitting there, unused, and can be developed. A fraction of it can be developed by these kinds of technologies. So coming back to our situation with the West, this is, I think, how we need to begin to assess the situation, right? We need to not just look for, quick gimmicks or quick solutions. I mean, it's a real long-term challenge and crisis that's developed over a significant period of time. And there's no getting around the fact that we need a vast increase in the water availability, an increase of the water cycle in the West as a totality, in a whole, right? There's no getting around that fact. And there's various ways we can do it. Again, so here's our augmented, human-controlled, human-managed, human-improved depiction of the water cycle, right? Desalination, we're bringing new flows, new stores of fresh water directly from the ocean onto land and into the activity on land. Weather modification, especially ionization-based weather modification, we're tapping the atmosphere directly, right? And we're bringing new storage of fresh water into the terrestrial system by increasing the rainfall, directing the rainfall where we want it, when we want it, through weather modification technologies. And we also have things like NWAPA as one example of river diversion, river transfer, where we're taking places where you have abundant amount of fresh water running off into the ocean, especially places where it's been used very little by biospheric or human economic activity, and redirecting some of that, in the case of Nawapa, 5%, very small proportion, down through other parts where the water's needed to augment the water cycle that way. And, really all of these proposals, all of these approaches can be done to interact with each other, and they're not separate siloed operations. They can be done in concert, by using weather modification to increase rainfall into basins that then provide water transfer systems, things like that. You can actually make sure that they all can benefit each other. So what do we actually need? If you just go by the water needs of the West, these are rough figures, but I'll just throw this out here as I think where the discussion really needs to be starting. And as Mike said at the beginning, thinking, not just about the next year, not just about this season, next season, but really thinking a generation down the line. What are we going to be doing now, investing now, to actually not just alleviate the crisis, but completely solve the crisis and create the basis for new growth, new development, new activity, generations into the future, right? That's what we need to be talking about. So, as we discussed earlier, the groundwater depletion, the rate of depletion of groundwater between the High Plains Aquifer, the Colorado River Basin, the Central Valley Aquifer, is about on the rate of the flow of the Colorado River itself, right? We're basically extracting the equivalent of a Colorado River out of groundwater, or it's being lost through natural causes, as is the case for some of the Colorado Basin activity. But we're basically losing the equivalent of a Colorado flow, the equivalent of a flow of a Colorado River consistently through groundwater losses. So you'd want to just alleviate that, to stop that. You'd basically need a new Colorado River into the West, into the Southwest, into the High Plains, to just provide, just to stop the depletion rate, just to get things back to break even. If you wanted to begin to refill those aquifers, which we should be doing, and actually put them back up to pre-development levels, make it easier to access groundwater supplies by refilling the aquifers, you probably want the equivalent of a second full Colorado River equivalent brought into these regions, right? Say if you wanted to refill these aquifers on the time scale of, say, a generation, 25 to 30 years, you would probably need another Colorado River. If you wanted to stabilize the existing water systems, the Colorado system, the California Central Valley system, and so on, you'd probably want, now you're talking about maybe the equivalent of a third additional Colorado River. And if you're talking about creating the basis for growth into the future, potentially another one. So you're talking about maybe 3 to 4 additional Colorado Rivers worth of water flow into the Southwest, into the High Plains, if you actually want to create the basis to really solve, not just solve the crisis, but create the conditions for growth. And that's possible. It's completely possible. It's completely doable. We laid the conceptual framework here for how to approach that kind of this kind of challenge. And I think we just need to take this perspective to this new political movement in the United States, the people fighting against the globalist destruction of our country, the people fighting for new manufacturing, new infrastructure in our country. These are the kind of things that this movement, these people should be looking at, discussing, and developing into more serious and rigorous proposals. So that's what I got. Happy to get into some discussion. I'm sure there's a number of thoughts on these issues. So let's go at it.